Howdy guys, how we doing? Well, we're going to start by talking off on energy. So, a couple different ways that I see energy, and I'll always be asking you, how do you see it? Bonneville Dam, we get our electricity from it. It's not like we catch the electricity from the water, we're doing things to it. The wind energy, it's not like we take the electricity out of the wind, but what we are doing is we're taking the energy that is there and we're just converting it into other things. This is me visiting the wind farm in Eastern Washington. Highly suggest going there. This one I want you to be thinking about as we go into today. How does this represent energy? A couple different things. How to quantify. We're going to start off with two simple ones. Potential energy. I want to specifically refer to this as gravitational potential energy. MGH, mass in kilograms, gravity is 9.8, 10 for us, height is the height off of the surface you're going to be at. So I have a 2 kilogram log, so I have a 2.0 kilogram log. Gravity is 10, height is 35. 700 joules. Kinetic energy, 1/2 mv squared. Kinetic energy, another way to say that, is motion energy, or energy of motion. So, if my daughter, who is 15 kilograms, is running at 3.2, I would say 1/2, 15 kilos. Velocity is 3.2 squared. Stick that in a calculator. And she has about 77 joules. So, now we start to play. A rock is dropped from a bridge. How much energy does it have at the top of the bridge? Well, the type of energy it has is potential energy at the top, which is mgh. Mass is 1, gravity is 10, height is 14 that it's going to drop through, and so that has 140 joules contained in Mr. Rock. Next question, how fast is it going when it hits? Let's talk about what type of energy it has. The type of energy it has kinetic energy when it hits. And it started with 140 joules, so it needs to have 140 joules when it hits. So I can say that the kinetic energy is 140. So I could say 1/2 mass velocity squared. So I get a velocity of some beautiful number. Now we pose to you the real questions. I have a river moving a certain velocity at the top of a mountain, so at the top of a cliff, and at the bottom it's going the same velocity. But right here, because of this height, I also had potential energy. So my question is this. The energy at the top should equal the energy at the bottom. Energy at the top, I have kinetic energy and I have potential energy. At the bottom, what do I have? Just kinetic energy. But it's going at the same speed at the top and the bottom. So where did it go? Think for a second before you predict. So, you've had a second to think. We need to talk about James Joule. What James Joule did is he looked at, if we look here, he had a bucket attached to a mass, and what the mass did was the mass fell, and it took its potential energy and it went to 0. And James Joule said that needs to go somewhere. And so what he had happen was it pulled on a string, and as it pulled on the string, it made this apparatus spin. It's kind of almost like an ice cream bucket. And what happened was these paddles made the water move, and then once the water stopped moving, all he did was took a measurement of the temperature. And guess what? The temperature of the water increased. And he saw that as he started to quantify the energy here, and he was quantifying the temperature change here, that he noticed that the energy that he started with equaled the energy that he ended with. So, back to our problem. So James Joule, on his honeymoon, they went and they found the velocities to be rather similar, and he says, well, the energy difference is this, so he stuck a thermometer here, and the temperature here was more than it was here. He showed that even in these big scale items that he can also show the same thing. So I'm on a roller coaster. When I'm up here at the top of my roller coaster, and as I think about going down there, So at the bottom I had all kinetic energy. As it come back up, it turns into potential. But then as it goes back down, I'm all kinetic. And as I go over these bumps and I go up and down, I see that my kinetic and potential change. So if I start at the top of a roller coaster with just potential, it turns into kinetic at the bottom. So let's do one problem, and then we'll call it a night. So a 100 kilogram roller coaster comes over a 20 meter tall hill at 5 meters per second. What is the velocity at the bottom of the hill? So start off by drawing your hill. So here is my cart, and I'm moving this way at 5 meters per second, and I am on a 20 meter tall hill, and the question is asking what is my velocity? Couple options. One, freak out. Two, I could say, you know what, I have potential energy and I have kinetic energy, and at the bottom I don't have potential anymore. I only have kinetic. And how do these two compare? Well, throwing out friction, they're going to be equal. So I can say the potential energy at the top and the kinetic energy at the top put together is going to equal my kinetic energy at the bottom. So mgh plus 1/2 mv squared. So my mass is 100 kilos, gravity, height is 20, 1/2 mass is 100, velocity is 5, and I get, well, those joules show up down here. And so I could set that equal to 1/2 mv squared, 21,250 joules. And so if I solve that out, I get a velocity of 20.6 meters per second. The next style of question that we could ask on top of this is, now it goes up a hill, I don't know, 5 meters high. What's its velocity at the top of that? Well, I already know the energy that it comes into it with, 21,250 joules. And that's going to have to equal the energy here. Well, you have to always stop and think about, what type of energy do I have? I have potential energy because I'm off the ground. I have kinetic energy because I'm moving. So it has to equal those put together. And so I look at 21,250 joules, potential energy, mass, gravity. My height now is 5 plus 1/2 mv squared. And now I have the mass is 100, gravity is 10, mass is 100. I can solve for the velocity. See you tomorrow in class. It's going to be a great day. Great day to be a Titan.